Okay, so think about this. You're trying to find your way somewhere, right?
Yeah.
And you've only got two lines to work with. Like think of an address on a street grid, uptown, downtown, or even latitude and longitude on a map, just two coordinates.
Right.
And boom, you've got a spot. Pinpointed it on a flat surface. Pretty basic stuff, really. The X and Y axis, been there, done that since, what, middle school?
Yeah, that familiar two-dimensional framework. It's like our geometry 101 works great as long as we're sticking to a flat plane.
But then, of course, real life has to come along and, well, throw a curveball.
Mm-hmm.
Literally.
Yeah.
I mean, think about a kite dancing in the wind, right?
Storage.
Or a submarine diving deep down.
Yeah.
They're not just moving left and right. They got that whole up, down, and everything in between thing going on. So how do we even begin to map that? How do we capture that out-of-the-page movement in our neat little coordinate system?
Yeah, that's the tricky part. We need to break free from those two dimensions. Bring in some reinforcements.
And that's what we're diving into today, the world of three-dimensional geometry, adding that crucial third dimension. We've got some great material to work with, excerpts from a math textbook, lays it all out. But we're not going to get bogged down in equations and jargon.
Right.
Our mission here is to make this stuff click. So you walk away with a clear picture in your head of how 3D space actually works and how we can navigate it, mathematically speaking, of course.
And this isn't just some theoretical brain teaser either. It's fundamental. Like the mathematician E.T. Bell said, mathematics is both the queen and the handmaiden of all sciences. Understanding this 3D stuff, it's the key to unlocking so much in science and technology.
Totally. Okay, so we're stepping off that flat page. What's the first thing we got to add to our 2D picture to, make it 3D? It's got to be more than just drawing another line on the same plane.
Right, definitely. We got to think bigger. In 3 dimensions, we're talking about 3 planes. And get this, they're all perpendicular to each other, intersecting at a single point. Like imagine the corner of a room where 2 walls meet the floor. That corner point. That's our starting point, our origin, as we call it.
Okay, so the 2 walls and the floor, those are our 3 planes. What do we call them? Do they have, fancy names?
We keep it pretty straightforward. We name them based on the axes they contain. So you've got the XOY plane. You're probably familiar with that one as the XY plane. Then we bring in the YOZ plane. And to round it out, the ZOX plane or ZX plane, sometimes you'll see it that way. These are the big 3, the coordinate planes that carve up our 3D space.
And where those planes intersect, those lines become our axes, right? The X, Y, and Z axes.
Exactly. The XOY plane and the YOZ plane, they meet up along a line. We call that the y-axis. More formally, Y prime OY. Same idea with the other two, YOZ and ZOX. They give us the z-axis, Z prime OZ. And finally, XOY and ZOX, those guys intersect along the x-axis, X prime OX. The key here is that these axes, they're all perpendicular to each other. Every single one forms a 90-degree angle with the other two. And that right there, that's what defines our rectangular coordinate system in 3 dimensions.
I'm trying to picture, it's like if you took 2 pieces of paper and held them up so they meet at a right angle, along one edge, then you slide a third piece in so it's perpendicular to both of them, right where all 3 edges meet.
That's a great way to visualize it. Now, if you think of the XOY plane horizontally like a tabletop, the Z prime C axis would be pointing straight up and down, perpendicular to that tabletop.
Okay, so now we got this orientation, but just like with our X and Y axis in 2D, we need to talk direction, okay? Positive and negative. How do we figure that out with these 3 axes?
We stick with a similar convention. Distances measured in one direction from each coordinate plane, those are positive, and the opposite direction, negative. So for the z-axis, moving upwards from the xy plane, along OZ, that's positive. Going downwards along OZ prime is negative. For the y-axis, think of it like moving to the right of the zx plane, along OY, that's positive. To the left, along OY prime, negative. And for the x-axis, it's all about moving in front of the YZ plane, along OX for positive. Behind it, along OX prime, that's negative.
Got it. And that point where everything comes together, all 3 planes and axes, it's still our origin, right? Or 0 point.
Absolutely. The origin, labeled O, in 3D space, its coordinates are 0, 0, 0, 0. It's our anchor point. Everything else is measured from there.
Now, I remember in 2D, those 2 axes, they divide the plane into 4 quadrants. What happens when we bring in this third dimension? Do we just get, more quadrants?
We get something similar, but yeah, we're stepping it up. 3 dimensions means 8 distinct regions. We call them octants. Think of it like slicing a cake. 3 cuts perpendicular, all meeting in the center. 8 pieces.
8. Wow, okay, that's quite a jump from 4. Do these octants have, specific names? How do we keep them straight?
We do. We name them based on, you guessed it, the signs of the X, Y, and Z coordinates inside them. The first octant, it's usually called XOYZ, or sometimes just octant by. That's where all three coordinates, X, Y, and Z, are positive. As we venture into regions where one or more of those coordinates becomes negative, we enter the other 7 octants.
So let's say if the x coordinate was negative, but the y and z were still positive, we'd be in a different octant.
You got it. That combination, negative x, positive y, positive z, that's our second octant. It's labeled X prime OYZ, or octant 2. You can actually map out all 8 possible combinations of positive and negative signs for X, Y, and Z. Each combo represents one of the octants.
In our source material, they even included a table that shows the signs of x, y, and z in each of those 8 octants. It's super helpful. You can look at those signs and know exactly where a point is hanging out in space. And it uses that prime symbol, like x prime, to indicate the negative side of the x-axis, which is handy.
Totally. That table, it's like a cheat sheet. And the prime notation, that's the standard way to show those negative portions of the axis. It's like a visual shorthand for understanding spatial location.
All right, so now we've got this framework, the axes, the planes, those 8 octants. But how do we actually pinpoint a specific point in all that 3D space? How do we get its coordinates?
Well, there are a couple of ways to think about it. Imagine you've got a point P floating somewhere out there in 3D. Now picture dropping a perpendicular line from that point straight down to the XY plane. Where it hits the plane, we call that point M, kind of like the foot of the perpendicular. Now from M, draw another perpendicular line over to the x-axis. Let's say it meets the x-axis at point L.
Okay, I'm visualizing it.
Great. So the distance from the origin O to L along the x-axis, that's your x-coordinate. The distance from L to M running parallel to the y-axis, that gives you the y-coordinate. And finally, the distance from M back up to our original point P, that's your z-coordinate. So point P, its address in space, is XYZ. And that order is super important.
I see it. It's like a vertical drop, then over, then back up. Make sense how those 3 distances define the exact location?
There's another way to visualize it too, using planes. Think about that point P again. Now imagine 3 planes passing right through it, each plane parallel to one of the coordinate planes. The plane that's parallel to the YZ plane, it'll cut the x-axis somewhere, right? Let's call that point A. The distance from O to A, that's your x-coordinate. Same idea for the other planes. The one parallel to ZX hits the y-axis at B, giving you the y-coordinate, and the plane parallel to XY intersects the z-axis at C, giving you the z-coordinate. Point P is right where all 3 of those planes come together.
Oh, I like that. It's like defining the point by its location relative to each of those main planes. And the source material mentions that these x, y, and z values, they're essentially the distances from that point to the y, z, zx, and xy planes, respectively. It ties it all together.
Exactly. They're the perpendicular distances, with a plus or minus sign to tell us which side of the plane the point is on, just like we talked about with the positive and negative directions along the axis.
Now, what about points that are, like, right on one of the axes? Or sitting in one of the coordinate planes? They must have some 0 values in their coordinates, right, to show they're not moving in certain directions.
Absolutely. If a point is chilling on the x-axis, it hasn't budged in the y or z direction. So its coordinates will always look like x, 0, 0. And a point in the yz plane, it has an x-coordinate of 0, so its coordinates are 0, y, z. Same logic applies to points on the other axes or in the other planes.
That makes total sense. The 0 is like a flag saying, hey, no movement here. The source even gives an example. If we have a point P at 2, 4, 5, and we want to find a point F that's in the plane parallel to the xz plane, it would have the same x and z coordinates, but its y coordinate would be 0, making it 2, 0, 5. It's like taking a slice through space.
Perfect analogy. F is in that plane parallel to xz, so its x and z positions are the same as P, but its y position is right on the level of the xz plane.
And there's this other example that asks us to figure out which octant points like -3, 1, 2, and -3 we're in just by looking at their signs. The first one, it's let plus plus. So that's the second octant, according to that table. And the second one, let plus lay, that puts it in the 6th octant. So handy.
It's all about those sign conventions we talked about. Easy way to tell where a point is hanging out without needing to visualize the whole thing.
And our source even gives us some exercises to try out, to really test our grasp of these concepts, like figuring out missing coordinates for points on axes or in planes, or looking at coordinates and saying, okay, which octant is this point in? Good way to solidify that understanding.
Yeah, those exercises, they're like little checkpoints. Make sure we're all on the same page before moving on.
So now we know how to describe where things are in 3D space. But what if we want to know the distance between 2 points? Like, how far apart are they? We need a 3D version of the distance formula, right? And I remember something about the Pythagorean theorem being involved here.
You're on the right track. The distance formula in 3 dimensions, it's basically the Pythagorean theorem, but souped up. If you have 2 points, P with coordinates by 1, y1, z1, and Q with coordinates by 2, y2, z2, picture a box, a rectangular box, where the line connecting P and Q is the main diagonal running from one corner to the opposite corner.
Oh, I see it. Those 2 points are at opposite corners of the box.
Exactly. The lengths of the edges of the box that meet at one of the points, let's say point P, those would be the differences between the x, y, and z coordinates of P and Q by 2 by 1, y2, y1, and z2, z1. Now, we get clever with the Pythagorean theorem. First, we use it to find the length of a diagonal on one of the faces of the box. Then we use that diagonal and the third edge to find the length of our main diagonal, PQ. And that gives us our 3D distance formula.
In the formula it's Celsius.
The distance between P and Q, we call it PQ. It's the square root of the sum of the squares of those coordinate differences. So square root of open parenthesis by 2 by 1 squared plus y2, y1 squared plus z2, z1 squared, close parenthesis.
Makes sense. It's like the 2D distance formula, but with that extra z2, z1 squared term under the square root. We added a dimension, we got to add a term, but of course the distance from the origin, 0, 0, 0, to any point, x, y, z, would be simpler. Square root of x squared plus y squared plus z squared.
Exactly. The origin makes things a bit easier.
Now, the source has some great examples of how to put this formula to work. We see it used to find the actual distance between 2 given points in 3D. And then there's an example showing how to check if 3 points are all on the same line, what we call collinear. You basically check if the sum of the distances between the first and second point and the second and third point equals the total distance between the first and third.
Right. Those examples show how powerful the distance formula is. Collinearity, it's a big deal in geometry, and we can check it easily with this formula.
And then there's an example where we have to figure out if 3 points form a right-angled triangle. So use the distance formula to calculate the squares of all 3 sides, and then we see if any combination of those squares fits the Pythagorean theorem. A squared plus b squared equals c squared.
Exactly. It's like we're taking the Pythagorean theorem and applying it to coordinates. Really handy for classifying triangles.
There's even an example where we're given a distance condition like pa squared plus pb squared equals 2k squared, where a and b are fixed points, and we have to figure out the equation that describes all the points P that satisfy that condition. That's a bit more abstract, isn't it?
It is. That example shows how we can use the distance formula to define shapes and sets of points using equations. All the points that fit that specific distance relationship, they form a particular surface in 3D.
And just like before, our source throws in some exercises. Gives us a chance to play around with the distance formula, calculate some distances, see how it all works in practice.
Practice makes perfect, right?
Right. Okay, so we can find the distance between 2 points. But what if we want to find a point that's like between 2 other points, dividing the line, connecting them in a certain ratio? That sounds like a job for the section formula?
Bingo. The section formula in 3D, it's just like the 2D version, but you guessed it, with an extra dimension. So let's say you've got 2 points, P with coordinates by 1, y1, z1, and Q with coordinates by 2, y2, z2. And you want to find a point, R, with coordinates, x, y, z, that divides the line segment PQ internally in the ratio mn. That's where the section formula comes in.
And what does that formula look like in 3D?
The coordinates of R are given by x equals mx2 plus nx1 divided by m plus n, y equals my2 plus ny1 divided by m plus n, and z equals mz2 plus nz1 divided by m plus n. Notice how it's the same structure for all 3 coordinates.
I see it. It's like a weighted average of the coordinates of P and Q, and the weights depend on that mn ratio. Now, what if R divides the segment externally in that same ratio? External division, easy fix. Just swap out n with n in the formula. So the coordinates of R become x equals mx2 minus nma1 divided by m minus n, y equals my2 minus ny1 divided by m minus n, and z equals mz2 minus nz1 divided by m minus n. Ah, so the sign of the denominator changes and we subtract instead of add in the numerator. Got it. What about the midpoint of a line segment? That's a special case, right? Absolutely. The midpoint, it's all about equal halves, a 1.1 ratio. Plug in n equals 1 and n equals 1 into that internal division formula, and you get the midpoint coordinates. X equals by 1 plus by 2 divided by 2, y equals y1 plus y2 divided by 2, and z equals z1 plus z2 divided by 2. Just the average of the x, y, and z coordinates of the 2 endpoints. Nice and simple. The source also talks about a form of the section formula where the ratio is k.1. When would we use that?
That k.1 form. Super useful when you've got a parameter k that can change. It lets you describe any point along the entire line that contains the segment PQ. The formula looks a bit cleaner too. X equals ky2 plus by 1 divided by k plus 1, y equals ky2 plus y1 divided by k plus 1, and z equals kz2 plus z1 divided by k plus 1.
And the examples really bring it home. We see how to calculate the coordinates of a point that divides a segment, both internally and externally. There's even an example where they use the section formula to prove that 3 points are collinear by showing that one point divides the segment formed by the other two in a specific ratio.
It's amazing how much we can do with this formula. That collinearity proof, it's like connecting algebra and geometry, showing how they work together.
And then we get to the centroid of a triangle. That's a point where all 3 medians of a triangle intersect, right? And it turns out we can calculate it directly from the coordinates of the triangle's vertices.
Exactly. If the vertices are by 1, y1, z1, x2, y2, z2, and by 3, y3, z3, the centroid, we call it G, has coordinates. G equals, open parenthesis, by 1 plus by 2 plus by 3 divided by 3, comma, y1 plus y2 plus y3 divided by 3, comma, z1 plus z2 plus z3 divided by 3, close parenthesis. The source even shows us how to derive this using the midpoint formula and the section formula.
It's like a chain reaction. Midpoint, then section formula, boom, we've got the centroid, and then we have that example where we have to find the ratio in which a coordinate plane, like the YZ plane, divides a line segment. The trick there is remembering that any point on the YZ plane has an x-coordinate of 0. So we use the section formula for the x-coordinate, set it equal to 0, and solve for the ratio.
Yeah, that's a classic application of the section formula. It lets us find where a line segment and a plane intersect, even without figuring out the full coordinates of the intersection point.
And, no surprise, we wrap up the section with some exercises to practice using the section formula in different scenarios.
Gotta get that practice in.
Okay, so the source finishes strong with some extra examples that show just how powerful 3D coordinate geometry can be. There's one where we have to prove that 4 points form a parallelogram. So we use the distance formula to show that opposite sides have equal lengths. And they even point out that to be a rectangle, the diagonals have to be equal too.
It's all about using these formulas to understand shapes in 3D. That parallelogram example, it's a good reminder that just because opposite sides are equal doesn't automatically mean it's a rectangle. We need those diagonals to be equal too.
Then there's an example where we have to find the equation that describes all the points that are the same distance away from 2 fixed points in 3D. And the cool thing is, that equation ends up describing a plane.
Yeah, all the points that are equally distant from 2 fixed points in 3D, they form a plane that perfectly bisects the line connecting those 2 points.
And last but not least, there's an example that kind of flips the centroid formula around. If you know the centroid of a triangle and the coordinates of 2 of its vertices, you can use the formula to find the coordinates of that missing third vertex. Clever, right?
It really shows how versatile the centroid formula is. We can rearrange it and solve for different parts.
It's amazing how we can take these algebraic tools and use them to describe shapes and relationships in 3D space. Makes you wonder how all this even came about. Lucky for us, the source has a little section on the history of 3D coordinate geometry.
It's a fascinating story. We usually think of René Descartes as the father of analytical geometry because of his work in 2 dimensions back in 1637. But 3D coordinate geometry, that came a bit later. Descartes had the idea of extending his system into 3 dimensions, but he didn't really flesh it out.
So who are the pioneers of 3D coordinate geometry? Who took that idea and ran with it?
In 1715, we have J. Bernoulli. He's the one who really introduced those 3 coordinate planes, the XOY, YOZ, and ZOX, the ones that form the basis of our system. But the first guy to really dive deep into analytical solid geometry, that was Antoine Perrin. He presented his work to the French Academy of Sciences in 1700.
Wow, that's earlier than I expected.
Right. And then, of course, there's Leonhard Euler. He was a math superstar. In his book, Introduction to Geometry, published in 1748, he really laid out 3D coordinate geometry in a systematic way, made it accessible to a wider audience.
It's interesting that it took some time to go from describing a flat plane to describing the 3D space all around us. And get this, the source even mentions how these ideas were later extended to spaces with more than 3 dimensions. Mind-blowing stuff.
I know. Our brains can only really picture 3 spatial dimensions, but math doesn't have those limits. It lets us explore higher dimensional spaces. Like Einstein's theory of relativity, it describes the universe in 4 dimensions, the space-time continuum.
It's amazing how far we've come, from those simple x and y coordinates to describing the entire universe. Okay, let's do a quick recap of what we covered in our deep dive into 3D geometry. We talked about those three perpendicular axes and planes that define our 3D space. We learned how to pinpoint any point using its XYZ coordinates and how those signs tell us which octant it's in. We even got two powerful tools: the 3D distance formula to calculate the distance between points, and the section formula to find points that divide line segments in specific ratios. That includes the midpoint and the centroid of a triangle.
Right, and we saw how to use those tools to figure out if points are collinear, if triangles are right-angled, and even how to describe planes and other surfaces using equations.
It's incredible how the system of coordinates, which might seem kind of abstract at first, lets us understand the spatial relationships all around us.
Totally agree. It's like a bridge between geometry and algebra, letting us use the power of math to solve geometric problems.
And here's a question for you, the listener, to ponder. If we can use this 3D coordinate system to navigate and understand our three-dimensional world, how might these same ideas be used to analyze and visualize data in higher dimensions? We can't picture those spaces, but the math still works. Think about all the technologies that rely on these principles: computer graphics, virtual reality, medical imaging, robotics, the list goes on. It's mind-boggling how these mathematical concepts shape our technological world.
It's truly fundamental stuff.
Well, that brings our deep dive into 3D geometry to a close. Thanks for joining us.
It was a pleasure exploring this with you. Always fascinating to see how these basic ideas have such a big impact.